Here we are, April 23rd, ready for another lesson. Still, this pandemic going around on this COVID-19 is not letting up. It's some pretty bad stuff. But I hear tomorrow they're going to start opening up some stuff, and that's a good thing. I hope it is. The ones that's high risk will still have to lay low and not get out and do too much and just try to be as safe as they can about catching this stuff. I don't think it's going to completely go away. I think before it's over with, we probably all going, somebody in the family is going to get it. Some it serves pretty bad and some don't have any symptoms. But this week we were supposed to do a term exam. I'm not much on this term exam the way we are on these videos, but when we resume class, we're going to do an exam and a practice test and be timed and something to get you ready for taking a electrical license test. I think that'll be more beneficial than us just trying to answer questions. I thought about doing half of the ones in the back of the book, but let's don't worry about that. We're going to move on to motors, motor circuits, and controllers. And then if you would, do the 37 questions in the back of that chapter and send them to me. We're getting into some stuff now that's a lot more interesting, and I think it's going to be better for you to look at, something that will interest you and get your attention and keep you motivated. Some of those other questions are hard to answer, and if you need to know that, if you're out in the field, you just have to look it up because you won't remember it anyway. But we still got to go through the curriculum, and it will help you on test questions and how to look them up. That's the most important thing. How to go about going to the code book and looking up grounding, like in Article 250, and just knowing where to go real fast on those exams. But anyway, we're going to start the video, and Susan Dean gave me a text. I sent it on to y'all, or sent me an email, that everybody needs to go ahead and sign up for the summer term. If you're having problems with that, she will help you, but she needs you to email her to give her permission, so she has written permission, and she'll take care of it for you. If you would, y'all take care of that tomorrow or just as quick as you can so that we can move that along. They got to have their paperwork in order. So if you would do that, and we're going to start this video now.
The motor circuits and controllers. Article 430, the scope. There's overload protection, we call them heaters. You have branch circuit, short circuit protection. You have branch circuit conductors. We have feeder conductors, and we have feeder protection. And this is a lot of what we're going to be covering in this particular part of the program. The definitions of 430.2 is, what is a controller? A switch or device that's used to start and stop a motor by making and breaking the motor circuit contacts. So all of these be ways to turn on and off a motor. And this is an example of devices that are not considered controllers. These devices often control the coil of a motor starter, but they usually don't carry all the current of motor branch circuit. Let's see, the only one that could be, now this right here, no, this would be a controller. Well, it all depends on whether it's a little 20 amp circuit, right? Breaking the circuit for a little sump pump.
Same thing with the pressure switch. The pressure switch could be the same way.
They could, okay, a little well, right?
Yes.
It's a contactor. You know, so you have, whatever's making and breaking the contacts, not push buttons.
In the water and wastewater
these are just,
business, we have
limit switches, and this is just making contacts to a control circuit. Well, then the control circuit
temperature,
is direct
flow,
power. That's
pressure,
that matters.
flow switches.
Motor nameplate versus FLC. This is not a motor class here. We have an entire video that deals with all kinds of motor conductor sizing and calculations. and we'll be covering that at another time. Actually, that'll be in next month. We'll be covering that. So I'm quickly going over motor calculations. This is something that you really need to get the calculations video to really understand all the calculations in motor. So let's go through it really fast. Ready for this? Motors have a nameplate, and they have a nameplate rating. And then you have the national code that lists the different currents of a motor. For the purposes of this program today, we will never be using the nameplate rating of the motor. We will always be using the motor code requirements because we're going to be using that to size the short circuit and ground fault protection, and we're going to be using that to size conductors. The nameplate is used to size overload, and we're not covering overload in this particular class. We cover that in our calculations class. Here's an example of a nameplate. The nameplate is calculated out with a function of this formula, having to know voltage, efficiency, and power factor, and we will never be using the nameplate for sizing the conductors and the protection device for short circuit and ground fault protection. Single motor. How do you size the wire to a single motor? Well, the code says take the conductors for a single motor are sized no less than 125% of the table full load current, not the nameplate value. And you go to the different tables and you look them up, and the table will give you a value. Let's go to a 1 horsepower motor. So let's go to the code book, and that's going to be 430.248. And there's going to be a table there. This is...
But I found out you can also go to the motor rating and not get it, because that's where they get
single
that rating
phase.
from.
And 250 is 3-phase. So using our example of single phase, 1 horsepower, 115. I like using the voltages that are going to be nameplate rather than nominal system voltages. 1 horsepower, 115 comes out to be 16 amps. And the rule was you size the conductor no less than 125% of the table current. The table current is 16 amperes. So then you take 125% of that. It comes out to be 20 ampere wire. And then you go to the code book, and we find out that 12 gauge wire at 60 degrees C is rated 20 amperes. So let's go to the code book. Let's go home. Let's go to 310.16, which is 310.15B16. I go to the 60 degrees C column, which is the very first column here. I need a wire rated 20 amperes, and that would be 12 gauge wire. But Mike, I thought you couldn't put, well, that's it. Let's stop right there. 20 amp. No, that worked out fine, right? Right, no conflict there. 20 amp wire. Now, if you have several motors, and you're trying to size the wire for several motors, let's say one motor is 22 amps, one motor is 42 amps. The code says the feeder conductor, which is a conductor for several motors, must be sized not less than 125% of the largest, which would be 42 times 1.25, plus the sum of the other motors on the same phase. Well, then there's one other one, which is 22. And if I do the calculation, I would take the 42 times 1.25 plus the 22. Oh, this example is showing what happened here. Oh, it is 2 examples. Okay, 2 motors. So 42 times 1.25 plus 22 plus 22 comes out to be 96. I'm going to round this off. However, Mike, let's start rounding this off. We'll start making this 97. In our textbook, we start rounding it off. 97. Have to find a wire that's rated 100 amps at, ooh. You're right. Which size the wire at 75 degrees C terminals. So 310.16, go to the code book, look it up, go to the 75 degrees C terminal.
Number 3.
I'm sorry?
Number 3.
Okay, without me having to go through it and find it again, it is a 3-gauge wire at 75 degrees C. And that's how you size it. Again, I'm moving really, really fast. This is an introduction if you're not familiar with this. This is not to take you into all the calculations as it comes to motors. So just kind of give you
That's
a
right.
feeling.
They're just trying
All right,
to
let's
get
move on.
you to where you're able to.
Let's go on to the short
size
circuit
the
and ground
motors,
fault protection of a motor.
right wire size for them.
When a motor starts, it starts at a high end rush current, and then as time goes by, it starts getting into the running. So you have starting currents and you have running currents. So we have to have a protection device that would allow the motor to start, but then we have to be able to protect the motor to make sure that there's not an overload condition. We do that by sizing the short circuit ground fault protection up here to allow this motor to start. And that protection is going to be sized between 150 and 300% of the motor full load current that's listed in the code book. This device right here is designed to protect against a fast rise current for a very short duration, and it responds very quickly. Where the heaters are designed to respond very slow rise current, long duration, and a slow response time. So let's do the calculations in sizing the branch circuit. A protection device that has a rating of setting not exceeding the value calculated in the table shall be used. Where the values of the branch circuit, short circuit, and ground fault protection device determined by the table do not correspond to the standard size fuses, then you can use, okay, possible setting does not, then we can go up to the next higher ampere size. Here we go. 1 horsepower motor. We've already determined it draws 16 amps. We size the wire at 125%. That was 20 amps. We then go to the code book at 60 degrees C, 12 gauge wire. So we're good there. The breaker is sized at 250% because we'd go to the table, 430.52. 430.50, is it 52? Yeah, 52C. Okay. Now we go to a table. And this table says inverse time breakers. You see here? They're all 250. We're not going to deal with wound rotor or DC constant voltage motors. So when you get to a breaker, you're going to use 250%. When you get to a dual element fuse, it's going to be 175. And when you get to a non-time delay fuse, it's going to be 300%. All my examples are circuit breakers, and circuit breakers are 250. So 16 times 2.5 gives me 40 amperes. I put a 40 ampere breaker on a 12 gauge wire. I have to tell you a story about this. I'm doing a seminar for the inspectors in Colorado, ICC, International Code Congress. And I was supposed to do a seminar on motors, and I thought I had it for 4 hours. And I found out I had an 8-hour seminar on motors. I'm like, oh my God. Nothing worse than an instructor having a lot more time left over and not being prepared for a lot more time. So I got into everything you need to know about motors. Starting currents and inductive reactance and the rise in the currents and how overloads work and how short circuit works and ground fault protection and how every single thing works. And over here, if you take a look at this graphic here, we're going to have heaters right here. This provides overload protection. This provides short circuit and ground fault protection. You get the overload and the short circuit and ground fault combined together, provides the protection of the motor, on and on. This is going to pick up, if you call, let's say the draw 16 and you draw 22 amps in there, it's going to pick this up. It's going to take care of that. But if you have a short, this breaker is going to see that. And listen, guys, we put 12 gauge wire here. You know, think about that. If you short two 12 gauge wires, you're lucky to trip the 40 amp breaker. You're hoping you don't take the 200 amp breaker in the house. How many guys have ever tripped a much larger breaker on an individual branch circuit? I'll tell you a story. I'll get back to this story, but let me tell you another story. I'm working in an equipment room, and I didn't have my time clock, the guts. But I got the wire coming in, I got the wire going out, but I didn't have a time clock. You know, whatever happened, the time clock's not there. I stripped the wire. I'm all ready to go. And I figured for the next guy to save him some time, I'll just strip the wire. So I took the two wires coming in on the line, put a wire nut on it, two wires going out, put a wire nut on it. Now, with the time clock, it's right there in the equipment room, right next to the service equipment and house panel. I go on, I find out later on, they couldn't get the main on the building to turn on.
Turn
They
it off?
turn on.
Oh, okay.
They couldn't turn the main on. I mean, they spent like days. Days. They go wham, wham, wham. And they said, the two wires that I had wired, 12-gauge wire, right next to the service with a house panel, when there was a short circuit, that 20-amp breaker, when you got into the instantaneous range, that did not trip. It dropped out the 400-amp main to the building. So that taught me a lesson. How many of you guys had that happen again to you? It taught me a lesson like, wow, when it comes to short circuits, a 400-amp breaker can protect 12-gauge wire at a very short distance. You know what I mean? So now take a look at the example here. 40 amps?
Well, why have them
Kidding me?
tied together?
That's nothing.
Peanuts.
You can knock that 40 amp breaker, not a problem, under short circuits and ground faults. But the problem would be what? Overload. That's why we have the overloads. You get the overloads, the short circuit ground fault. So now I explained it. First thing in the class, hey, how many guys don't like this 12-gauge wire 40 amp breaker? Everybody raised their hand. Okay. Wow, I'm going to teach you. At the end of 8 hours, I said, how many guys? I mean, honestly, I did a really good job. Okay. I mean, I did a really good job. And I'm feeling pretty good. At the end of the day, I said, how many guys still don't like it? Everybody raised their hand. Nothing changed. And I'm like, I just wasted one day of my life. So there are people, like let's wrap it here. There are people that have a major problem. Let's look at the illustration here. You size the wire to 125%. You size the breaker to 250%, which means your protection is always going to be 2 times the size of the wire. That's how the numbers work, no matter how many times you try it. And this protects the motor, the conductors against short circuits and ground faults. That protects the overloads, and we're fine. We'll move on.
What about from here
Now,
to here?
If the calculation
It
doesn't
shorts out
correspond to
right
the standard
there.
size,
You're
then
not
you use
in,
the next size up
in
protection
compliance.
device. Here's
I
a
don't
2
like
horsepower
it either.
motor. It draws 12 amps. And we're going to use a non-time delay fuse. And that's going to be 3 times. So 12 times 3 gives you 36. Doesn't correspond to the standard size protection device. And then we had the exception that says, well, if it doesn't correspond, go up to the next size. I then could put a 40 amp dual element fuse. Just giving you some understanding of how these rules work. All right, feeder protection. 430.62. This is interesting. The protection, the feeder supplying a specific motor loads and consisting of conductor sizes on 24, which is what we did for 2 motors, shall be provided with a protection device having a rating or setting not greater than the largest setting of the branch circuit, short circuit ground fault protection device for any motor by the feeder, plus the sum of the full occurrence of the other motors. So, here we go. This motor draws 28. This motor draws 17. How do you size protection for 17? Well, you go 17. It's a circuit breaker times 2.5. Let's do that right there. 17, just to double check my number here. 17 times 2.5 equals 43. So if it equals 43, I have to go with size protection device. 45. Okay, the other one is going to be 28 times 2.5. It came out to be 70. So I have a 70 amp breaker here, and then I have a 45 amp breaker there. Now this feeder protection is to be not greater than 70, which is this size right here, plus that full load current is not to be greater than 87. Therefore, we go with an 80 amp protection device. This is the hardest thing for me to teach. For some reason, people want to go to 90 because they're thinking that next size up. But it doesn't. It's just simply, it's not a matter of next size up. It's a matter that the rule, well,
It says not greater than.
it just, go back here. It's just that the rule says it's not greater than. Well, if it's not bigger than 87, it's not 90, Brian?
Well, I think, the simple thing that people are getting hung up on is that you've already added the buffer in there to start the motor on the biggest motor. So you have more than enough buffer in there for any motor that's smaller than the largest motor, no matter what you do. You use that same amount of buffer for any motor all the way down.
Exactly right. The theory is this. You would need a 70 amp breaker to be sized to allow this motor to start. Is that right?
Yep.
you need a 40 amp breaker here to allow this motor to start. Right?
Right.
Now, watch the logic here. If this motor starts first, that means you got 17 amps going. Is that right?
Yep.
Then this motor starts. That means you have 17 plus 70. You have 87. You follow the logic? Not bigger than 87, 80. But what about if this motor started first? This motor has 28, right? Then you'd have 28 plus what? 45. That gives me 73, not bigger than 70. Now, if both motors start at the same time,
There you go.
okay, well, now we might have a problem because now you're going to have 70 plus 45. So the assumption is that, the motors are all running except the largest one. Then the largest one starts is the logic there. Motor control circuits.
See, they're just
The
assuming.
disconnect for the control circuit. A disconnect for the motor control circuit is required where the control circuit isn't tapped from the controller disconnect. In other words, if you're running a control circuit to your controller, so where's my control circuit? Oh, right here, right here. Here's my control circuit. Well, then I need to have a disconnect for that control circuit. And it must be adjacent to the controller. So my disconnect, so here's an example. Here's my disconnect, and it's adjacent. I need to be able, when I work on the controller, I need to be able to know the control circuit. If it's not tapped on the line side, how do I turn off my control circuit? And that's what I was telling you about that hospital. In a hospital, I had all these air handlers, and I tried to put in the control for energy management in there, and there was no information. There was no disconnect, and that's a danger there. Motor controllers. Controller rating. When you're turning a controller which is making brake contacts, controllers other than circuit breakers and molded case switches must have a horsepower rating not less than that of a motor. So when you have a controller which is going to be other than a circuit breaker and a switch, has to have a horsepower rating. Now, horsepower rating means that the motor is designed to take 6 times the lock rotor current rating of the switch. That's what a horsepower rated switch is for. Sorry?
The switch is designed.
What did I say?
You said the motor's designed to
Okay.
take the current from the
The
switch.
switch is designed to be horsepower rated to take 6 times the rating of whatever that largest horsepower rating of the switch. Well, then, Mike, how come circuit breakers and molded case switches don't have to have horsepower rating? Because circuit breakers and molded case switches are already listed at 6 times the lock rotor current of the motors. So that's why a circuit breaker, it's suitable for the application. It's already designed to be taking care of that 6 times. But if it's not a circuit breaker, it's not a molded case switch, well, then you have to have a switch that's horsepower rated.
Is that what that HACR that
No.
we used to see on there? What is that?
The HACR, heating, air conditioning, refrigeration, was that kind of yes and kind of. It's kind of like SWD, HID rating of
Okay.
switches.
So it's the mechanical, how it's built.
Well, there was a characteristic that took place on heating and air conditioning refrigeration loads. And then what happens, air conditioning contractors were required to mark it on making either a fuse or HACR rated circuit breaker. Then what happened was we started using fuses because there were no hacker breakers. Well, then the circuit breaker guys at that time weren't in bed with each other like they might be now with Eaton owning, Bussmann fuses as well as, Cutler hammer gear. Then the circuit breaker guys had to get their circuit breakers listed and tested for HACR. All circuit breakers today are HACR rated.
Right.
So they don't have to be marked. And because of that, the UL standard changed that none of the equipment has to be marked HACR. That doesn't mean you're not going to get something that's marked HACR. The problem is if it's marked HACR, the circuit breakers will not be marked necessarily HACR because they are HACR. You only mark something when it's like, well, maybe something is and something isn't.
Right.
You got some stuff from Tom Dimitrovic there that has that information about the hacker breakers.
Okay.
You might have looked at the SWDs, and if
Yeah,
you go
yeah.
further in there, you see the HACR information there.
Okay.
So, controllers have to be horsepower rated unless they're a circuit breaker or a molded case switch. Now, a simple toggle switch or general use switch, the motor controller, like a switch right here, can be a general use snap switch for motors rated 2 horsepower or less, where the motor full load current is not more than 80% of the ampere rating of the switch. So if you have a 15 amp rated switch, I wish we could zoom in on that a little closer. Oh, it says 15 amps at 80% maximum. It actually has a name, looks like a nameplate might be in there completely. Maximum 12 amp. So you can use little snap switches for that application. Now this then would be the controller in that application. Disconnecting means. Disconnecting mean requirements in 430.102. Motor controller disconnect. Now, a motor controller is what makes and breaks the contacts. A disconnect is required for each motor controller, and it must be located within sight from the controller. So here's your controller. This is right here, but it must be within sight of the controller. So that's fine. Now, this is a violation because this is the controller of the time clock. And this disconnect is not within sight of that controller. The controller disconnect must disconnect all circuit conductors of the controller simultaneously. Here's my controller. And the violation here is that it's not within sight. Mike, get rid of this text here because that's actually confusing things. It doesn't belong here. Here's your controller disconnect. The violation is that it's not within sight. Now, a motor disconnect. The controller disconnect can serve as the motor disconnect if it's located in sight from the motor. So here's the controller disconnect. And if the controller disconnect is within sight of the motor, then I don't need to have a separate disconnect for the motor because the controller disconnect can serve as the motor disconnect. Now, you need a disconnect within sight of the motor, and that's another way to do it. Just simply put a disconnect within sight of the motor, put a disconnect within sight of the controller. These are the rules of being within sight. Now, let's have some exceptions. I'm wondering, is there an exception for the controller disconnect? Can I have an exception that the controller disconnect doesn't have to be in sight if it's capably unlocked in the open position? 430.102. 430.102.
I hope that's clear as mud. What I usually do is put a disconnect at the motor.
An individual
Regardless of
disconnecting
where
means
the
shall be
controller
provided for
is.
each controller and shall disconnect the controller.
So you
The
can kill it,
disconnecting means shall
work
be
on it,
located
and
within
change
sight
it
from the
out.
controller. One is over 1,000 volts. Single disconnect can be permitted. The group of
Usually your
coordinated
motor
controllers,
starter is right there at
disconnect shall be
your
located within sight.
MCC.
The disconnection
So
means
it's
shall
a
be
disconnect.
cannot be required
Then
to
you
be
out
sight.
in the field, when you go
Wow.
like in another room,
You
there's a
have to
disconnect.
have the disconnect within sight of the controller, and there is no exception. That would be a violation. Now let's go with the motor. The disconnect for the motor must be within sight of the motor, or you can use the disconnect for the controller if it's within sight of the motor. Now there is a provision to have a disconnect
That's a
for
good
the
way to
motor,
do it.
not
You put
within
your
sight
disconnect,
of the motor.
then you control the
But take a
controller
look at
and the
this
motor.
real strange rule. Let's go over to the motor disconnect. All right, let's go here. A disconnecting means for a motor shall be located within the side of the motor and the driven machinery. The controller disconnect is permitted to serve as the disconnecting means for the motor if it's within sight. Then we have an exception for the motor disconnect. And here's what it says. Oh,
They were below you right there.
I was below it over here? I skipped it, didn't I?
The controller disconnect, exceptions, yeah.
Now this is the motor disconnect. The disconnecting means for the motor shall not be required under condition A or B, which follow, provided that the controller disconnecting means is lockable in the open in accordance with 105. So go over here. Okay. This disconnect here for the controller has to be within sight of the controller. There's never an exception there. But you have to be able to lock the disconnect for the controller before you can use the exception. Here's what the exception says. You don't have to have a disconnect within sight of the motor. You don't need a disconnect within sight of the motor. Such a disconnect for the if it's impractical. Yeah, that's not practical. Like, what do you mean if it's impractical? Yes.
Can you scroll up just a little? This isn't controller disconnect?
Well, this is an exception to 1 and 2.
Okay.
And the disconnect means for the motor, and it's dealing with the motor. Because 1 and 2
Let's see.
is dealing with the motor condition.
Okay.
You can use a controller disconnect for the motor, but it still have to have a disconnect with inside of the controller back on A.
Right.
Now, a disconnect's not required with inside of the motor if it's impractical. Can you think of any examples where it would be impractical to have a disconnect with inside of the motor? Eric?
Pond pump.
Yeah, middle of a pond, middle of the fountain, right? Down at the bottom.
Right.
A motor down at the bottom of a well.
Yeah, I can't get down to the motor to see the disconnect.
Nope. So if you have a well, a submergible well, a pond. Hey, by the way, something for you to know. What do you call those motors that? Yes. Okay, a submergible motor, right? Cannot be used for
A fountain in a lake.
no. A submergible motor cannot be used in a lake.
Yeah.
You cannot use a submergible motor in a lake.
Yeah, a couple kids died in Lake Travis in Texas some years ago because in Texas there's a exemption from Texas electrical law for well drillers. And so some people who lived around the lake thought, oh, well, I'll just put some submersible wells under my dock and I don't have to comply with the laws. Well, ground fault path wasn't made up and some swimmers died.
You see, a motor that goes in a well knows that there's no public people around, right? In other words, it's in a well. It's in a well casing, it's in the ground. If there's a fault, but if you take a submergible motor and you put it in a lake and then there's a fault, and submergible well motors, if you look at the instructions, they'll tell you, shall not be installed in anything other than an enclosed well. So there is no other exception. I talked to somebody where it's really cold, and what happening is they really needed to put the pressure and the static pressure, I guess, for that kind of stuff. They say, well, Mike, there's no other way for us to get the irrigation besides using a submergible well in a lake. And I said, well, you can't. Okay, let's go back here. So you don't need a disconnect within sight. Heinz?
How about building on what Eric said? How about a lift station? Lift station where you've got the motor all the way down the bottom, maybe even a couple of them.
Yeah. So you can't have it within sight. And that's fine.
And it's not within sight.
Right. So, or introduce additional hazards. In other words, hey, having a disconnect by the motor would introduce a hazard. You're like, what? Here, they tell you what the hazards are. Examples of increased or additional hazards include, but are not limited to, motors rated in excess of 100 horsepower. I don't understand it. I don't know, Eric. I guess if you have a very large motor, you don't want to have a disconnect next to the motor, and you don't want to open the disconnect next to the motor. Is that true?
That's correct. There are some compressors that cost millions of dollars that if you have a disconnect next to the motor, that there are very rigid start and stop sequences to the motor. And having a disconnect next to the motor can destroy $1 million very quickly.
Submergible motors, we talked about that. Motors associated with adjustable speed drives.
Well, like
Brian,
that'd be
I
an
think this
exception
is
to the
where
rule.
would this
You have a
this
piece of
disconnect?
equipment
They've been
like
saying
that.
that you really can't have within sight of the motor. Where would that be located? That'd be a problem.
There's a lot of applications.
No, but I'm saying where in the circuit would this be the problem?
Where in the circuit
Yeah,
would be
is it
the problem?
on the supply side of the variable speed drive or between the
But it's between the drive and the motor.
right? I just want to get people to
Yeah,
understand.
I'm sorry.
here.
I
It is
misunderstood you.
an adjustable speed drive.
Right.
It's because we're talking about the disconnect for the motor.
Right.
An adjustable speed drive is not a motor.
Well, and you can't, I shouldn't say you can't. I don't want to say that. Most of the time, it's not smart to put a disconnect after a drive. That needs to be ahead of the.
That's what this is saying.
Right.
It would induce additional hazards. So
Yeah.
adjust speed drives, or maybe has a classified location.
Sure.
Don't put the disconnect in a classified location. So there are some provisions, but it's very, very limited. Eric?
Yeah, sometimes even if the code doesn't require a disconnect by a motor, sometimes you see them anyway when the controller or the source is out of sight, simply for the zero voltage checks. So when an electrician goes out there to work on it, say you have to do a zero voltage check to verify that the circuit's de-energized. It's easier to open up a disconnect and do that than it is to open up the motor connection box.
Okay. All right. Very limited application. You're ever going to have a
Right.
disconnect. So you're going to have one with inside of the controller. You're going to have one with inside of the motor. Now let's talk about where do you have to locate them. Oh, by the way, the disconnect for the motor controller and the motor must open all ungrounded supply conductors simultaneously and be designed so it won't close automatically. You can't use a time clock as a disconnect, because unless there was a setting in the time clock that would allow it to be a disconnect and rate it as a disconnect, and you turn it off, because you turn it off and then all of a sudden you're working on it, and then what happens? The clock mechanism turns on because the line sign is energized and it turns off. So we have to be very careful. Brian, let's make a note that there's resolution on this graphic here. Now, the readily accessibility. I like this. I think this is what we should be doing with switches. When rules have disconnecting means, they should tell us what to do with the readily accessibility. We saw that in the electric space heating, it had to be what? From a readily accessible place. This one says either the controller disconnect or the motor disconnect required by 43102 must be readily accessible. Now, I guess this is where we have to kind of lean on that switch rule, don't we?
Yeah.
Not located more than, but you know what I'd like to see, Dave? If we're looking for the switch rule to apply to 6 foot 7 inches, unless it's adjacent to the equipment and readily accessible, I'd like that information to be placed in 430. Not that I have to know that, okay, well, this is a switch also, so now we got to go to
Even
404.
for air handlers.
I'm sorry?
Even for air handlers.
Yeah, in other words, I think the requirements on the height of switches and readily accessibility should be all
Should
the
be
disconnecting means when
readily
they're required, so they don't have to go to some general rule. But here's the deal here. The guys in switches, I don't know who handles switches, but would you agree the guys in switches don't know anything about the disconnecting means for all the appliances?
Right.
Because they're just switch guys. So the people who should be responsible for the disconnecting means in those other code articles should have their switches, their disconnecting means, and the completeness of it at that particular location, and not depend on some boilerplate switch requirement in 404.8. Disconnecting mean ratings. The disconnecting means itself has to be rated. Motor circuit switch, a listed motor circuit switch, a circuit breaker, or a molded case switch. Because why? They're automatically listed for lock rotor. They're automatically tested to the standard for that. Then we also had the condition of the switch could be used as a controller. Well, that topcoil switch could also be used up to 2 horsepower as the motor disconnect. You can use a horsepower rated attachment plug-in receptacle having a horsepower rating not less than the motor rating, and can be used as the motor disconnect. Brian?
Yeah, they actually have, when you start dealing with horsepower rated attachment plugs, they're almost all the brands out there have them with built-in, they actually are disconnects. You actually flip a handle and it actually disconnects it before you unplug it. So they're actually really nice, really, really great.
Very convenient.
Yes.
Okay, before I finish up motors, just a brief little tutorial, kind of get you started in there. The calculations were very fast. You really need to get a calculations video to understand those type of calculations, and why is the 40 amp breaker okay on 12 gauge wire, and how come you don't limit the breaker to 20 amps on air conditioning or motor loads and what have you. Okay, let's do Article 440, just a couple more articles to go here. Air conditioning and refrigeration equipment.
I'm going to stop it right here.
And dirty.
And like I say, if you would answer the 37 questions in this chapter, send me the pictures. If you haven't, or if you're not up to date on the questions, please do that and send them to me so we'll all be caught up. We're getting into motors. I would love to be able to use some of the trainers at school, and then we could get into the motor controls and schematics. That's at a later time, but we're going to continue on without doing an exam, and we'll get caught up on the testing and the practice test and the questions I'm putting together. And that's going to about do it for this week. And y'all work safe. Stay out of the coronavirus sites, and just keep doing what you're doing. I appreciate your patience, and we'll catch you next week. Have a good one.